Hey guys, so this idea actually came to me while I was messing around in Figma, and I started wondering how do these polygon Boolean operations really work under the hood? So I thought, why not try implementing it myself and see what's happening behind the scenes? There are a bunch of different algorithms out there for this stuff, but for this video, we're going to focus on one, a simple classic one, the Sutherland Hodgman algorithm. I'll get it working cleanly here, and later I'll show more. This algorithm is mainly used for polygon clipping, which means it's perfect for finding the intersection between two polygons, basically the overlapping region where both shapes meet. It's not meant for things like union or subtraction because those require more advanced logic to combine or cut shapes apart. So for this part, we'll only focus on intersection, understand how clipping works, and then in future videos, we'll move on to more advanced algorithms that can handle the full set of Boolean operations like union, subtraction, and even complex polygons with holes. So what exactly is intersection? It's the area shared by both polygons. If two shapes overlap, the intersection is only the overlapping part. That's different from union, which combines everything from both shapes, and subtraction, difference, which removes the overlapping part from one of the shapes. This is where the Sutherland-Hodgman algorithm comes in. It was originally made for polygon clipping. Take one polygon as the subject and another as the clip polygon. Then trim the subject edge by edge so what remains is fully inside the clip polygon, i.e. the intersection. There are also several other algorithms and techniques people use for polygon Boolean operations. I'll quickly list some of the common ones so you get a sense of the landscape. We'll explore these in future videos. First up, Weiler-Atherton. It's great for complex polygons and super useful when you need union or difference operations along with intersection. Next, Greener-Horman, a popular algorithm for polygon clipping and Boolean operations that handles a lot of tricky cases pretty well. Then there's Vati, or general polygon clipping, and libraries like Clipper are actually based on this one. It can handle polygons with holes and even self-intersections, which is why it's widely used in production. After that, we've got the Martinez, or Martinez-Rueda, plane sweep algorithm. It's an efficient clipping algorithm used in a few libraries. I'll be honest, I haven't worked with this one before, so I'm a bit curious to see how it performs. Next is the plane sweep or sweep line approach, along with winding rule techniques. These come from the broader computational geometry toolbox and are used to build more general Boolean operations. And finally, we'll look at some robust libraries like clipper.js, Martinez, and others. These are perfect when you need something battle tested and production ready instead of building everything from scratch. All of these are worth digging into, but each one comes with its own weird edge cases and messy details. Implementing them properly takes time. There's a lot of testing to do, plus handling holes, self-intersections, floating point nastiness, and other little surprises. So I'll cover them one at a time in future videos. Hope you guys understand. It's going to take a bit of effort to get each algorithm working cleanly. For now, let's keep it simple. We'll implement Sutherland-Hodgman, get intersection working, and really understand clipping step by step. After that, we'll move on to difference, union, and then the fancier stuff like Weiler-Atherton and Vati in later videos. Alright, so now let's start the code. I'm assuming you already know how to set up a pixie.js project. Just run npm create pixie.js at latest, and once it's ready, clean up the default code so we can start from scratch. In some of my previous videos, we've already gone through this part. I've added the links in the description if you want to check them out as well. We begin by importing everything we need: application, graphics, container, and text from pixie.js, and a few functions: clip poly, point, subject poly, and Sutherland Hodgman clip from our boolean.ts file. Those imported functions handle all the polygon logic. We'll dive into them later when we start exploring the clipping algorithm itself. Next, we create an async function and initialize the Pixie app. This sets up a canvas that resizes automatically with the browser window and attaches it to our HTML container. Then we grab the clip polygon button from the DOM and create some variables for managing our shapes and drawing layers. We add all of these to the stage. That's how Pixie manages what gets drawn on screen. The next few lines set up a small info panel at the top right corner. It has a dark transparent background and a text field inside it. This info box displays the coordinates of the subject polygon, the clip polygon, and the resulting intersection points. It helps us visualize what's going on numerically when we move or modify shapes. Now we move on to the Clip Poly button click event. When you click this button, it takes the current intersection points and creates a new draggable polygon on screen. We draw it with a semi-transparent orange fill and set its interactive flag to true, which makes it respond to pointer events. Then we define the drag logic using pointer down, pointer move, and pointer up. When the mouse goes down, we mark it as dragging and record the offset. When the mouse moves, we update the polygon's position. When the mouse goes up, we stop dragging. It's a simple reusable pattern for interactivity inside pixie.js.
Next is the Update Info Box function. This is where we format and display the polygon data. We first clear and redraw the background, then update the text to show 3 sections: subject, clip, and result polygons, with all their point coordinates listed neatly. This function is called every time the polygons are redrawn, so the info stays in sync with what's visible on screen. The redraw function is one of the most important parts of this file. It clears all the graphics layers, redraws the subject and clip polygons with their own colors, and then calculates the intersection by calling Sutherland Hodgman clip function with subject poly and clip poly. The intersection points that come out of this function are stored and used to draw the result polygon in a red shade. Finally, we call Update Info Box so the text panel shows the new coordinates.
In short, redraw keeps everything consistent. It updates visuals and data whenever something changes. After that, we handle the global dragging for both polygons. When the user clicks anywhere on the canvas, we check if the pointer is inside the clip polygon or the subject polygon. Whichever one contains the point becomes the target. Then as the pointer moves, we calculate how far it moved since the last frame and add that offset to every vertex of the selected polygon. Finally, we call redraw function again so the shapes move visually. When the pointer is released, dragging stops. It's a simple approach that directly updates the underlying vertex arrays, keeping the geometry and visuals in sync. We also have a window resize listener that calls app.resize function and redraw function so that the layout and polygons stay properly aligned when the window size changes. Now let's look at the utility functions at the bottom. The point and polygon function checks whether a point lies inside a polygon. It uses a simple ray casting algorithm. It casts an imaginary line from the test point and counts how many times it crosses the polygon edges. If the count is odd, the point is inside. If it's even, it's outside. This is a standard, reliable method used in computational geometry for hit testing. The next one, draw polygon, is our helper for rendering polygons. It takes a graphics object, a list of points, and a few optional style parameters. It clears the old drawing, sets the line style and fill color, then moves through each point to draw connected lines, and finally closes the path. If fill is enabled, it also fills the shape with the given color and transparency. This function keeps our main drawing logic clean and makes it easy to reuse for multiple layers. And that's it for the main.ts file. We now have an interactive pixie.js setup with 2 polygons, a subject and a clip polygon, and a visual result of their intersection computed using the Sutherland Hodgman algorithm. So, now we're in the most important section of the project, implementing the Sutherland Hodgman algorithm. Before we start writing the logic, let's first understand the idea behind it. The main goal of this algorithm is polygon clipping. That means we take one polygon, which we call the subject polygon, and another polygon, which acts as the clip polygon, and we trim the subject polygon so only the part that lies inside the clip polygon remains. In short, this gives us the intersection area between the 2 shapes. So how does this algorithm actually think? The core idea is brilliant, and is basically a divide and conquer strategy. Instead of trying to figure out the complex intersection of 2 weird shapes all at once, Sutherland Hodgman does it one step at a time. First, it takes the clip polygon, the cookie cutter, and breaks it down into its individual edges. Second, it clips the entire subject polygon against the infinite line defined by the first clip edge. This gives us a new intermediate polygon. Third, it takes that new polygon and clips it against the infinite line of the second clip edge. And then at last, it just repeats this process, feeding the output of one clipping step as the input to the next until it's gone all the way around the clip polygon. The final polygon that's left is our answer. So how does it clip against one infinite line? This is the heart of the algorithm. For each clip edge, let's say it goes from point A to B, the algorithm walks around our subject polygon, looking at one segment at a time. Let's say a subject segment goes from point S, start, to point E, end. There are only four possibilities. Case 1, inside, inside. Both S and E are inside the line. This is easy. The whole segment is good. We just save the endpoint E. Now you might ask why we are putting the E, why not both? It's a key part of how the algorithm works so efficiently. We only add E, the endpoint, because S, the start point, was already added in the previous step. Think of it like tracing the polygon. The algorithm builds the new clipped polygon one vertex at a time. In the previous iteration, let's say it was from point P0 to S. S was the end point. Since S is inside, as we know from our current step, that previous iteration would have ended by adding S to the output list. It would have been either case 1, in to in, or case 3, out to in. Now in our current iteration, we are processing the segment S to E. Our output list already contains S. Since the whole segment S and E is inside, we just need to add the next vertex of our new polygon, which is E. If we added both S and E every time, our final polygon would have duplicate vertices. So, the rule, only add E, is how the algorithm correctly connects the dots, adding each valid vertex only once as it walks around the shape. Now let's move to the next step. Case 2, inside to outside. S is inside, but E is outside. The segment is crossing the line on its way out. We need to find the exact intersection point I. We save that intersection point I, and we throw away E, since it's outside. Case 3, outside to inside. S is outside, but E is inside. The segment is crossing the line on its way in. This is the key one. We find the intersection point I, we save I first, and then we save the endpoint E, which we know is inside. Case 4, outside to outside. Both S and E are outside. The whole segment is outside. We don't save anything. By applying these four rules as we walk around the subject polygon, we build a new list of vertices, and that new list becomes the input for the next clip edge. It's really clever. Okay, let's dive into the code and see how this works in practice. First, we have two crucial helper functions, isInside and segment intersection. Let's look at those. This function tells us if a point PT is on the inside of an infinite clip edge defined by edge A and edge B. How it works, it uses a 2D cross product. This is a math trick that calculates the direction of the turn from the vector A to B to the vector A to point. The sign of this calculation tells us if our point is on the left or right side of the line. For this algorithm to work, our clip polygon must be defined in a consistent order, like clockwise.
The line return cross less than or equal to 0 means we're defining inside as being on the right-hand side or on the line as we walk along the edge, which is correct for a clockwise clip polygon. Next function is segment intersection.
What it does, this finds the exact intersection point between our subject segment P1 to P2 and our clip edge P3 to P4. How it works. This is standard 2D line segment intersection math. It first calculates a denom, denominator. If this is 0, the lines are parallel, and we just return null. The most important part is calculating t. T is a value that tells us where on the P1 to P2 segment the intersection occurs. If t equals 0, the intersection is at P1. If t equals 1, it's at P2. If t equals 0.5, it's exactly in the middle. The check if t is greater than or equal to negative epsilon and t is less than or equal to 1 plus epsilon is just asking, is this intersection point actually on our segment? We use a tiny eps or epsilon to handle tiny floating point errors. If it is, we use t to calculate the exact x and y coordinates and return the new point.
If you want a dedicated video where I break down this function and the math behind how line segment intersection actually works, let me know in the comments. I didn't want to make this video too long, so I kept it short, but I can definitely make a full explanation video if you want it. Alright, this is the part where everything finally clicks together. This is the moment the whole algorithm actually starts doing its magic. Let's break it down in a super clean, super easy way. First, we grab the whole subject polygon and make a copy of it. Think of this as our working shape. This is the one that's going to get trimmed down little by little. Second, we jump into the main loop. This loop runs once for every edge of the clip polygon. Basically one round of trimming for each side of the cookie cutter. Third, we do a quick handoff. We take whatever survived the last round and call that our new input. Then we reset the output so we can rebuild it fresh. Simple, clean, no confusion. Fourth, we figure out which edge of the clip polygon we're working with right now, from point A to point B. And yeah, there's this little wraparound trick that makes sure the last point connects back to the first one. That way the clip shape stays a perfect closed loop. Fifth, and this one's actually important, we set our starting point, S, to the last point of the input polygon. Why do we do that? Because the first segment we want to check is the one that goes from the last point back to the first point. That keeps our loop intact and makes everything behave correctly. Next, we jump into the inner loop. This is where the real action happens. We walk through the polygon, one segment at a time, and apply our simple rules. We pick our endpoint, E, and now we're looking at the segment from S to E. Then we check if both points are inside the current clipping edge. Now let's go through the cases. Case 1, in to in. Both points are inside. Easy win. We just add the endpoint to the output. Case 2, in to out. We're leaving the shape, so we grab the intersection point and add that. Case 3, out to in. We're entering the shape, so we add the intersection first and then the endpoint. Case 4, out to out. Both points are outside, so we add nothing. We just move on. After every segment, we slide forward by making S equal to E. The end of the last segment becomes the start of the next one. And when the big outer loop has trimmed against every edge of the clip polygon, the output list now contains our final, perfectly clipped polygon. And that's it. That's the whole Sutherland Hodgman algorithm. Super elegant, surprisingly simple, and honestly kind of cool once you see it in action.
So I hope by now you've got a clear understanding of how the Sutherland Hodgman algorithm works. It's honestly one of the best algorithms to start with when learning polygon clipping, because it's both simple and visual. You can literally imagine those clip edges acting like infinite laser lines that trim the subject polygon one edge at a time until only the part inside remains. We've seen how each clip edge runs through the subject polygon, how we decide which points stay, which ones go, and how intersection points are added exactly where those laser lines cut across the edges. Once you get this intuition, the logic behind the algorithm makes total sense. It's like step-by-step sculpting, where each clip edge shaves off the parts that lie outside. Now the next few algorithms like Weiler-Atherton, Vatty, and the plane sweep methods are a bit more advanced. They deal with more complicated cases like polygons with holes, self-intersections, and multiple overlapping regions. So give me a little time. I want to implement and test them properly before covering them, so I can explain everything clearly and with good visuals. If you've made it this far, thank you so much for watching and learning with me. If you've got any questions, suggestions, or if something didn't make sense, just drop it down in the comments. I'll either reply directly or make a follow-up video explaining it better. And as always, the GitHub link for all the code is in the description. Feel free to clone it, experiment, or modify it your way. That's all for this video. Stay curious, keep experimenting, and I'll see you soon with the next part, where we'll move into the next algorithm and push this polygon clipping journey even further.